All right, year 11, I have 4% and I need to ASAP Rocky describe collision theory as fast as we can because we didn't get to do it today. All right, so investigate the role of the following on, not even my pen, the following on collision theory. So activation energy, number of collisions, and molecular orientation. We have quite a bit to get through. Collision theory, a nice little recap. When we have two particles colliding with each other, we need them to have a certain energy that they overcome in order for the reaction to happen. Now, this just depends on what your particles are. Let's say, for example, for A and B, I need at least 1,000 kilojoules per mole in order for this reaction to happen. If I can overcome this energy, then I'm going to form my products. If I can't, not going to form my products. And that's the basis of collision theory. So the activation energy, the minimum energy required for the reaction to happen. Okay, the energy threshold, as we like to say. So here is our normal activation energy profile. So we look at our reactants down here in the bottom. This is the number we were talking about before, right? So the 1,000 kilojoule per mole. I need to overcome it for my products to form. Over here, right at the top, first of all, once I've reached this number, all good. I'm going to form my products. But also we see here it's written transition state. Transition state is basically just talking about, well, this and this reacting to make this. We're going to have to break bonds and make bonds. You're in the transition of those. Somewhere in the middle between breaking and making them. And then we have enough energy. We're transitioning from our reactants to our products, right? The amount of kinetic energy that a colliding particle needs to displace an electron, right? That's how we can define our activation energy. Now, activation energy is influenced by two things: our temperature and our catalyst. The easiest way to analyze this is looking at a Maxwell-Boltzmann distribution graph. So when we look at this graph, this shows us the number of molecules and the kinetic energy. So if I'm going to grab my nice container, I'm going to have all my molecules in here, right? What this graph essentially wants to teach us is, let me grab these molecules. These molecules have this much energy. And these molecules have this much energy. And these molecules have this much energy. So within my container, not all my particles are at the same amount of energy. They have different amounts of energies. This is a very oversimplified version of this. But they all have different amounts of energy. And what's interesting is that a certain amount of them will actually be able to overcome the activation energy threshold. So this is my minimum requirement. If you overcome it, yes, reaction is happening. All of this, we're not seeing reactions happen. Okay. Now, this gets important when we start looking at temperature and catalysts, and you are expected to know, I should probably put my iPad on charge. You are expected to know the minimum amount of energy required for the diagram, and then be able to kind of interpret the diagram and draw your own kind of version. Probably an inaccurate version, but draw your own version. Let me explain what I just said, because I kind of got distracted with charging my iPad. So here we've got temperature 1 is less than temperature 2. All right, let's look at temperature 2. So this one, temperature 2 is going to be hot, and this is going to be cold, right? Common sense. I heat up my particles. My particles have more kinetic energy now because they've been heated up. Well, does that affect my activation energy? No. My activation energy, now what's important first of all before I move on to this, is this area under each graph. Even when I change it, it needs to remain the same. So under the brown graph and under the black graph, it has to stay the same because we're not changing the number of molecules. The number of molecules is always going to be the same. We're just looking at how temperature affects them. All right, so let's have a look here. back to my point. So we said, hey, this is hot, this is cold. All right. My activation energy is kind of like this woman overcoming a hurdle. It's going to remain in the same place. This is my hurdle, and this is the minimum amount of energy I need to overcome. Well, if I heat up my reaction, and that will be T2, this is me heating up my reaction, then obviously I'm giving it more energy. More energy, then more particles colliding. Well, that makes sense. More particles colliding. Well, I'm seeing that. Under the black graph, I'm seeing a lot more particles overcoming the activation energy because we've increased their energy as a total. And I can also see that over here. Majority of them have a higher energy. But when we lower that temperature, less energy, then overall there's less particle collisions. And if there's less particle collisions, we can just see generally they skew more towards the left side because they have less energy now. And obviously, if we're looking at our threshold, now we have less amounts of molecules overcoming the activation energy. Therefore, surely, if there's less molecules overcoming the activation energy in T1, then there will be less successful collisions in T1 than in T2. Okay, that's our summary of what we're trying to say. You decrease the temperature, then you're also going to decrease the number of successful collisions. What about when it comes to catalysts? When it comes to catalysts, it's a different story. Now you're looking at the activation energy and you are lowering that hurdle. So here we couldn't change the hurdle. We're stuck up here. Now we're bringing it down. All right. With our catalyst, before I get into that, let me tell you what's going on with our catalyst. Our catalyst is just an alternative pathway. So I've got these two reacting. Instead of taking them into this nice reaction right here, why don't I take them on a nice journey and react them with something else and then break down that something else and blah, blah, blah. So it's an alternative path. In my alternative path, I form an intermediate. So here it's showing you. You've got hydrogen peroxide. Essentially, we want to form water and oxygen. But instead of doing that in one reaction where it's hydrogen peroxide and water and oxygen, let's just make an intermediate, a middleman. This middleman right here, this is the reason why I'm able to have a reaction with lower energy requirements. That's our alternative pathway. So our catalyzed reaction is going to have a lower standard than our uncatalyzed reaction. Therefore, we can reach that bar even easier. We can overcome that bar faster, and therefore we increase the rate of our reaction. All right. Collision frequency is different. Collision frequency is just looking at how many particles do you have colliding within a chemical system. This one's basic. This one's influenced by temperature, concentration, surface area, and pressure. Obviously, if they're colliding more, if there's a higher frequency of collisions, then they're going to be reacting more. Like if you put them in and this goes back to gas laws. This is essentially how we rationalized all of our gas laws. We said if we put them in a higher concentration or pressure, then they're more likely to meet each other. More likely to see each other, and therefore they're more likely to react. Now, if we're comparing the effect of, and I was going to put this out for you guys to answer, but just going to go through that. If we're comparing the effect of temperature versus surface area, concentration, and pressure, temperature has something unique. It's special. It's a special little one. The special thing with temperature is we are linking it to our activation energy and the kinetic energy that the particles have, because essentially temperature is the only one that's able to increase or decrease our kinetic energy. The rest of them don't do that. The rest of these just increase our collision frequency because they're able to meet more often, right? Just because they're tied up, packed in, or maybe there's more of them, they're able to meet more often. Kinetic energy is the only one that's linked with temperature. All right. The last thing we're looking at also is molecular orientation. With molecular orientation, we need them to collide in a specific alignment. We are so specific about this. Have a look at A and B reacting. Well, if this butt is facing this way, that's fine. But if it's facing this way, not going to happen, buddy. Well, that's the idea here. This is going to be influenced by temperature, concentration, surface area, and pressure as well. Just because increasing any of them is also going to increase how often they meet, right? Or increase the number of collisions, right? But just the idea that you need to know for here is you have to have a specific orientation. If the orientation is more favorable, let's have a look at this one, for example. It's showing you where it's not favorable and where it is favorable. If the orientation is favorable, then it's more likely to react. So a greater number of collisions means more particles collide in the correct orientation. That's pretty common sense. All right. And that's it for collision theory.